So far, we have only seen how to design low-pass filters, but very often we will also need to use high-pass filters, band-stop or band-pass filters. But even if this is the case, usually we design a low-pass filter nonetheless. Once the low-pass filter design is done, then we use a suitable frequency transformation to transform the designed low-pass filter into the desired high-pass, band-pass or band-stop filter. Let's assume that we have a low-pass filter that's described by the transfer function h of s. Here it is important now that the low-pass filter transfer function should be given in real s. Then this can be transformed into a high-pass filter by substituting s such that we get h of omega c low-pass times omega c high-pass divided by s. Instead of getting the frequency response of the low-pass filter h of omega, omega is substituted by minus omega c low-pass times omega c high-pass divided by omega, such that we get the frequency response of the high-pass filter. Of course, omega c LP is the cutoff frequency of the low-pass filter, and omega c HP is the desired cutoff frequency of the high-pass filter. We can illustrate this frequency transformation for a low to high-pass filter by plotting the relationship of the original frequency range of the low-pass filter versus the frequency range of the high-pass filter. We see that the cutoff frequency of the low-pass filter becomes the cutoff frequency of the high-pass filter. In the low-pass filter, all frequencies between 0 and the cutoff frequency of the low-pass filter are in the passband of the filter. This frequency range is transformed to frequencies that are above the cutoff frequency of the high-pass filter, hence the passband of the high-pass filter. The frequencies in the frequency range above the cutoff frequency of the low-pass filter form the stop band of the filter. This is transformed into the frequency range between 0 and the cutoff frequency of the high-pass filter, hence creating the stop band of the high-pass filter. This plot illustrates the frequency transformation of a low-pass to band-pass filter. The behavior of the low-pass filter at its cutoff frequency is transformed to the behavior of the band-pass filter at its first cutoff frequency or lower cutoff frequency and to its second or upper cutoff frequency. The frequency range between minus and plus the cutoff frequency of the low-pass filter, which forms the passband of the low-pass filter, is transformed into the frequency range between the two cutoff frequency and hence forms the passband of the band-pass filter. And the frequency range for frequencies above the cutoff frequency or below minus the cutoff frequency is transformed to the frequency range below the lower cutoff frequency or above the upper cutoff frequency to form the stop band of the band-pass filter. In formulas, the relationship is given by the frequency of the low-pass filter is equal to the cutoff frequency of the low-pass filter times the upper cutoff frequency of the band-pass filter times the lower cutoff frequency of the band-pass filter minus the new frequency range of the band-pass filter divided by the new frequency range of the band-pass filter times the difference between the two cutoff frequencies of the band-pass filter. The last plot illustrates how to transform a low-pass filter into a band-stop filter, also called a notch filter. The behavior of the low-pass filter at its cutoff frequency is again matched to the two cutoff frequencies of the band-stop filter. The behavior of the low-pass filter for frequencies in its passband is transformed into the frequency range of the passband of the band-stop filter, which is below the lower cutoff frequency or above the upper cutoff frequency. And the frequency range in the stop band of the low-pass filter, this is all frequencies above the cutoff frequency of the low-pass filter or below minus the cutoff frequency of the low-pass filter, is transformed into the stop band of the notch filter. That includes the frequencies between the lower and the upper cutoff frequency. In formulas, this can be expressed as omega LP, the frequency range of the low-pass filter, is equal to the cutoff frequency of the low-pass filter times the frequency range of the new band stop or notch filter times the difference of the cutoff frequencies of the notch filter divided by the product of the two cutoff frequencies of the notch filter minus the new frequency range of the band stop or notch filter.